So in the previous lecture, we introduced the notion of connectedness, and one of the most basic spaces is the interval, are the closed intervals a comma b inside R. So today we will prove that these are connected. So let's just begin. So proposition, the interval 0, 1 is connected. So proof. So let us assume that zero, 1 is not connected, right? So then there exists non-empty open sets U and V such that these are also disjoint. 0, 1 is the disjoint union U, disjoint union V, right? Okay, so we may assume, so one of these contains 0, so we may assume that it is in U. 0 belongs to U. Right. So let us consider the set S is equal to those x in 0, 1 such that this entire interval 0x is contained in U. Right. So if we were to make a picture, so this is our interval 0, 1. Right. Our U may be some combination of open sets, and V is also some open subset, so that U and V are disjoint, right? So we are assuming that, so let's say U is both, yeah. It could be a complicated open set, we don't know what it looks like, but it contains 0, right? So this S is defined as the set of all those x's such that this entire closed interval 0x is contained in U. Okay, so clearly S is non-empty because 0 is in S, right? Because as the closed interval 0 comma 0, this is just equal to singleton 0. This is definitely in U. Right. Now let A be the supremum x. So we take the supremum over all elements of A. Yeah. So we claim that A is in U. Yeah. So by the definition of supremum, right? By the definition of supremum, there is a sequence of xn's in X such that xn's converge to X. Xn's converge to A, sorry. So let's call this AN. So now as U, as V is open, as V is open in this interval 0, 1 and U is the complement of V, this implies that U is closed. in 0 1, right? And since U is closed and each an belongs to U, each an belongs to U because an is in S implies 0 comma an is subset of U. In particular, an also belongs to U, right? So therefore, and ans converge to, so U is closed, an belongs to U, and ans converge to A. These together imply that A also belongs to U. Okay, so A, we have proved that A is in U. So now note that as an is in S, this implies this interval 0 an is in U by the definition, which implies when we take union n greater than or equal to 1, 0 an, this is also contained in U. Okay, so now observe that. So if we make a picture, so this is our point A, and we have this sequence of ans, A1, A2. They don't have to increase necessarily, but they will converge to A. They are going to get closer and closer to A. Yeah. So now if we take any point y, which is strictly less than A, right? So then we can choose an epsilon neighborhood around A which does not contain y, right? And for all n sufficiently large, the ans will be contained in this epsilon neighborhood, right? So therefore, this implies that for any y in 0 comma A, any y which is greater than or equal to 0 and strictly less than A, we will have that y belongs to 0 comma an for n sufficiently large, right? So this shows that 0 comma A, this half open interval, is contained in U. And plus we have proved that A is, as we have already proved, that A is in U, right? So this implies that the interval 0 comma A, this closed interval, is contained in U. Okay. So now we claim that A has to be equal to 1. Okay. If A is not equal to 1, so if A is strictly less than 1, right? So once again we have 0, we have 1 here, and let's say A is somewhere over here, then there is epsilon positive such that the interval A minus epsilon comma A plus epsilon intersected with 0 1, right? So A minus epsilon intersected with 0 1, this is contained in U. Okay. So we can choose A plus epsilon such that A plus epsilon is strictly less than 1. We can do this as A is strictly less than 1. So this implies that A comma this half open interval is contained in U, which implies that 0 comma A we already know is contained in U, so therefore the union epsilon is contained in U. So which implies that 0 comma A plus epsilon is contained in U, which implies that, so this is epsilon by 2, this interval A plus epsilon by 2 is completely contained in U. Okay. So but this contradicts the fact that, so this implies that A plus epsilon by 2 is in S, right? But this contradicts the fact that A is the supremum of elements in S. So therefore, thus A is forced to be 1. Right? In particular, so this implies that this entire interval 0, 1 is contained in U, which contradicts non-emptiness of V. Right? Thus, 0, 1 cannot be disconnected. So this implies that 0, 1 is connected. So this completes the proof. Okay. So let us make a remark. So a slight modification. Of the above proof. Shows that when A and B are two real numbers such that A is strictly less than B, then the closed interval A comma B is connected. Okay, so we just have to imitate the proof, and that's easy. So this is left as an exercise. Okay, but we can do this in a simpler way, which we will just see, which we will see immediately. So not immediately, a little later. So as a corollary of this, let us show that R with the standard topology is connected. So proof. If not, then we can write R as the disjoint union of two open sets where U and V are disjoint, non-empty open subsets. Okay, so we can choose any A in U and B in V, and without loss of generality may assume that A is strictly less than B. Right? So then intersecting this relation R is equal to U disjoint union V with the interval AB, this implies AB intersected with U disjoint union AB intersected with V. Okay, yeah. So both sets are non-empty. As A is contained in AB intersection U and B is contained in AB intersection B. Right? So this gives this shows that AB is disconnected. The interval AB is disconnected. Which is a contradiction. Right? Because both these are open subsets in the subspace topology on AB, and here AB has the subspace topology. So, yeah. So therefore, we have written the interval AB as a disjoint union of two non-empty open subsets. Yeah. So which contradicts the fact that AB is disconnected. Okay. So as a corollary of this, right? So let us try to understand what are all the connected subspaces of R. Right? So let y be a non-empty connected subspace of R. Right. So then y is one of the following. Right. So basically it's an interval. So a comma b are real numbers with a strictly less than b. Okay, let's just take less than equal to b, right? Yeah, either this or a comma infinity okay. So let us prove this. So the idea is simple. So we define a to be infimum y in y, and b to be supremum y in y. Right. So here we have a real line and our y is some subset. So we take the infimum and supremum of all elements in y. Right. So then a is less than or equal to b. So note that a and b, they are allowed to be plus minus infinity. So if a is equal to b, so this clearly implies that y is just the single test set A. Right. So I'll leave this as an exercise, right? And clearly in this case, y is connected and equal to this interval a comma a. Okay. So if a is strictly less than b, then we claim that the open interval a comma b is contained in y. Okay. So if not, then there exists c which is contained in this open interval such that c does not belong to y. Right. So a is over here and b is over here, and there is some c such that c is not in y. But then this will imply that we can write y as y intersection minus infinity comma c disjoint union y intersection c comma infinity. So let's check that this is non-empty. Right. So as a is the infimum of elements in y, there is a sequence in y which converges to a, and since a is less than c, so there will be elements of the sequence in the interval, elements in the sequence which are strictly less than c. So this shows that this is non-empty, and similarly this is non-empty. Right, because b is the supremum of elements in y, so there will be a sequence of elements converging to b, and since b is strictly greater than c, so almost all members of the sequence will be greater than c. Right, so thus this gives a contradiction. So this contradicts the assumption that y is connected, because we have written y as a disjoint union of non-empty open subsets. Right. So thus the interval a comma b is contained in y. right? Y has the subspace topology, and in the subspace topology, both these sets are open, right? And also notice that Y is contained in A comma B, right? As A is equal to infimum of elements in Y, and B is equal to supremum of elements in Y. Right? Thus we have A comma B is contained in Y is contained in A comma B. Okay, so this part is relevant only if A and B are finite, and from this, we can easily conclude that Y has to be of the type mentioned. Okay, so this is left as an exercise. Okay, so this result, it gives us a description of the connected subsets of the real line. Okay. So next we want to see a very useful proposition which talks about how the interaction of connectedness and continuous maps. So proposition. Let f from x to y be a continuous map. Okay. So assume x is connected. Right. So then f of x, which has a subspace topology from y, is connected. Okay, so the proof is easy. So let's see. Right? If not, then there exists open subsets U and V such that f of x is the disjoint union of f of x intersected U and f of x intersected V. Okay. So these are open subsets in Y. U and V are open subsets in Y. So let me emphasize that U intersection V need not be empty. Right. So what is given? We are assuming that f of x is disconnected, which means there are two open subsets in f of x, but every open subset of f of x is of the type f of x intersected with U. So therefore we can only say that f of x intersected with U and f of x intersected with V. These two open subsets of f of x are disjoint. So need not be empty. So this is just a word of caution. Okay, so and both these f of x intersection U and f of x intersected with V are non-empty. Okay, so note that this implies that we can easily check that X is equal to F inverse of U disjoint union F inverse of V. So this is an easy check. An easy check. Okay. So moreover, as f of x intersected U is non-empty, this implies F inverse U is non-empty. And similarly, F inverse V is non-empty. Right? So as F is continuous, both F inverse U and F inverse V are open. Yeah. So thus we have written X as a disjoint union of non-empty open subsets. But this contradicts the connectedness of X. Right? So thus f of x is connected in the subspace topology. Okay, so we will see several useful applications of this proposition that we proved. So we will end this lecture here.